Welcome to this quantum security and defense presentation, Quantum Key Distribution, a Telecoms Perspective, and thank you for being a valued member of our community. Mateusz Ozimek is a Polish physicist finishing his PhD in the field of complex systems physics. He currently works as an R&D expert at Exatel, the Polish telecommunications operator. He is part of the team working on the SEQRET project, which aims to develop secure and industrialized quantum key distribution systems for European telecommunication networks. He also works as a research and teaching assistant at the Warsaw University of Technology.
Okay, so thank you for your introduction. So when I was preparing those slides, I thought about many things. So starting from the physics basics of creating a quantum network to the quantum internet, and I realized that when I want to cover all the topics which I would talk about today, it would be not 15 minutes, rather maybe 1 hour or 2 hours lecture. So I chose 3 topics. Namely, I will start with the test beds, which are currently in Poland. Then I will move to the physics basis of the quantum network and the field which I cover in Exatel, and and also the field which we cover in the SEQRET project. And then I will talk a little bit about the business perspective, because in the end of the day, we would like to earn money using QKD and quantum networks. So, as Anna said, Exatel is a Polish telco operator. It deals more with business to business partners, not business to customers. We have quite big fiber infrastructure, over 20,000 kilometers of fiber optics. We have more than 4,000 telecommunication hubs. We are also present not only in Poland, we have points of presence in other parts of Europe. But why we deal with the QKD? We deal with because we create solutions which should be at perfect 100% secure. But this is not the ideal physics model that could work in 100% all the time. So the 100% is the goal, which we would not reach in the future, but we want to be as close as we can. And I think from the part of the cybersecurity and this part of Exatel, which deals with critical infrastructure in Poland, the QKD and quantum networks are a very interesting topic to cover. So to begin with, I'm the part of the SEQRET project crew in Exatel, so I will start with this project. So this is project funded by Digital Europe program. It is the leader of the consortium is the KeyQuant company from Germany. We have partners from all over the Europe. So there is the COSO, Rodon Schwarz, also from Germany. For application and test beds of QKD, we have PSNC from Poland, but also CESNET from Czech Republic. From the component side, there is also Smart Photonics from the Netherlands. So this is the broad consortium from all the parts of the Europe. So this project aims to develop a secure quantum key distribution systems, and we are focusing on the industrialization, scalability, and certification of QKD devices. There will be 2 types of devices prepared as a part of the SEQRET project, and those QKD devices are based on the continuous variables QKD, so CVQKD approach. We have basically we have 2 approaches to the QKD: DVQKD, where we deal with the photons, and the CVQKD when we use the continuous beam of light and we encode the information, for example, in amplitude or phase in this beam. As I said, 2 kind of devices will be prepared. The first one will be at the TRL-8. It will be industrial quantum key distribution system. And we are also focusing on the next gen QKD using PIC approach, so integrated photonics at the TRL-7. And there is the part that Smart Photonics do. And we are focusing not only on the devices, we are focusing also for the certifications and the certifications and preparing also all the necessary documents for a common criteria certification. The SEQRET project will unify all the necessary scientific papers into one single security proof. The part which I'm responsible of in Exatel is the part which deals with the full network system integration. We would like to test those devices in real time, in real conditions, not only using fibers in labs. We would like to try the real fibers in real conditions. Like today in Poland, we have a really bad weather, so we are interested on topics such as using aerial fibers, or if the temperature influences somehow the Q rate of the QKD devices. We are in partnership with two Polish subcontractors for test field tasks. Those companies are Quantum Optical Technologies from University of Warsaw and Startowa from the Mikołaj Kopernik University in Toruń. Those are companies which are spin-outs on the universities, and we have a pretty good partnership with them. This is the project which I'm currently involved in, but we have also the other projects which are linked with the EuroQCI initiative. So I will start with NLPQT project, which was held in 2022. So it was about establishing a long-distance QKD link between Poznań and Warsaw. They used trusted node architecture and fiber infrastructure for secure quantum communication. They also created a dedicated QKD network within the city to use it as a test bed for the R&D things. And this NLPQT infrastructure was incorporated then to the Pioneer Q project, which I will describe in a second, which enables the expansion and the QKD infrastructure and testing those QKD applications on the national scale. Moving on, the Pioneer network, which is the backbone of the Pioneer Q project, is a network which is operated by Poznań Supercomputing and Networking Center, PSNC, which is the owner and operator of this network. It includes approximately 9,000 kilometers of fiber optics. So it is quite a big network. It is integrated with European JANT network, and those ownership, this network is owned by one PSNC. This full ownership allows quick adaptation to quantum communication technologies. So they support QKD integration and with the EuroQCI structure, and they are involved in building this whole EuroQCI network in Europe. So the project objective of Pioneer Q project is to establish a QCI backbone between 5 HPC centers in Poland. It started last year in 2023. The duration of this project is about 30 months, and they're gonna test a number of use cases. For example, QKD and blockchain technologies integration, a medical data hub, and also the QKD adaptation for public institutions. And the infrastructure, as I was informed by the leader of this project, it will be more than 1,500 kilometers of intercity QKD links. They will build the nodes in main city of Poland, and they will be ready to cover the QKD metro system installations. So also the national security agencies are involved in this project, so they will be connected by dedicated QKD systems. And as I was informed in November, so I think in December is also up to date, the use cases development phase is in progress. Moving on, there is not only, this EuroQCI thing in Poland, so it happens quite a many things in the case of quantum communication. For example, one of our partners, namely Startova, is also involved in the project or projects regarding the satellite QKD. So they won last month the ESA project for the multidimensional free space quantum key distribution. Also from the business side, there are many test beds in Poland. For example, one of those test beds which were published, so you can read something about in the internet, is about Netia, which is one of the Polish telco operator, and Nokia, which tested QKD security between data centers in Poland. But you know, this is the delicate thing, so there are not so much information in the internet. But I'm pretty sure that there is much more than only this this test from the business side. So this was the first part. What is going on here in Poland in the case of quantum communication? So moving on, this is the one slide. I think many of you know what is QKD. So the QKD uses concepts which are known from the quantum mechanics, and it is a method to generate and transmit keys which are secure and can be used for the symmetric encryption. In Exatel, we are focusing on we are focusing on the optical fiber as a transmission channel, but we are also thinking about open space. But I think this is in the future. There are many well-known QKD protocols. So I talked a little bit about DVQKD, so the protocols which are based on the single photon detection, and also about CVQKD, so the measurement of continuous variables. And from the perspective of the telco operator, the CVQKD is better because it operates much better than DVQKD with common telco stuff in our networks. So you know this picture very well. This is the BB84 protocol. I think I'm not gonna go into the details here, but I have a little more details in how to do a quantum key distribution in a telco network. To begin with, we are focusing on standards. So for us, QKD standard and standardization is very important because we want to have a pretty well standardized and certified devices. We need to prove that those devices are safe. There are no obvious side attack channels for those devices, and we can sell the keys to our clients. So there are many standardization going on in the world. So for example, ETSI standards, which are published in the last few years about the description of QKD use cases, the evidence of QKD security, and also the integration of QKD in disaggregated architectures. So I think it's very interesting that the SDN approach is pretty well seen here. So there are many scientific papers which proves that the SDN paradigm is very good for the QKD networks. Which is very important for us is the interoperability of different QKD systems and components from different vendors, because when we want to expand our network, we would like to buy the cheapest and the best stuff available right now. So when the network will be only composed of the components from one vendor, it would be pretty hard for us to expand this network and to make a good profit. So this is very important from the case of telco operator. And moving on to more technical details, this is one very important thing. It is very important in Exatel that we would like to have a coexistence of quantum and classical channels. So we are not interested in using dark fibers, because dark fibers cost a lot more money than combining quantum and classical communication. So we want to lower the cost of the QKD to have a better margin of profit. So, for example, we are studying the coexistence of quantum and classical channels in case of DWDM using DWDM technology. I will go into details based on the scientific papers. So, for example, how it works, the DWDM is a technology which allows multiple optical signals to be transmitted simultaneously over one optical fiber. So we have, like in this picture on the right above. So we have, on the x-axis, we have the wavelength. We have a band of the wavelength. And for example, in C band, we have a wavelength starting from around 1550 to 1600 nanometers. So each lambda is a dedicated channel, and the optical signal are modulated into different lambdas, for example, within C band or L band or O band also, which is a little bit around 1300 nanometers. And those signals are combined into one single stream using optical multiplexer. And then those signals are transmitted over optical fiber. And on the other side, at the receiving end, those signals are separated using the multiplexer. So why we use it? Because it maximizes the use of existing fiber optic infrastructure. And there is the problem. How we can put, for example, a CVQKD device and for Alice and Bob, and send the quantum channel using the coexistence with the classical channel. Why is this? It's very hard to do so, because every active component which is present in a classical telco network, for example, at the amplifier, it amplifies the signal, so it makes a measurement of the photons which are approaching. So we have the no cloning theorem. Each measurement influences the quantum state of those photons. So we cannot use active components. It's very hard to cover this. Those components inputs a broadband noise of quite a high level, so it kills every quantum key distribution signal from the fiber. So we need to bypass them somehow. Also, the MUX and the DeMUX devices inputs a little bit of noise. So when we calculate each part of the network and we sum up the level of noise, it's hard to prepare some kind of coexistence, but it's doable. I will show the results of one of the papers from one of the conference which studies this problem. The other problem which we have as a telco operator is the trusted node architecture. So because of the attenuation of the optical fiber, we are limited by the length of the link. Let's say the maximum length is about 100 kilometers. So what to do when I have two locations which are far away from each other, for example, by 500 kilometers? We can build a trusted node architecture. So we have intermediate relay points which extend the transmission range, but they receive quantum keys, decrypt them, and transmit them. So the problem is that when you have access to this relay, you have the access to the key. So they need to be physically secure to prevent unauthorized access. And they can be potential target for attacks, such as physical tampering, side channel exploits, or insider threats. So physical tampering, you can build a tamper-proof device, but there are also quite a few known side channel exploits, I'm not gonna go into the details, but the BSI in Germany prepared a very good document regarding the side channels, each known side channel for the quantum key distribution protocols. And this is the thing which limits the use cases because of the length, and that we cannot, you need to have a trust for the operator, which gives you the keys. On the right side, you have some kind of sketches which shows the trusted node architecture. So we have a QKD transmitter. We have intermediate nodes which do XOR operations on the key. Also, there is not only the case is not only about the QKD infrastructure layer. We need to also build a management layer. So we need to have a QKD controller. We need to have the key management system where we store those keys. And above that, we have application layer where we have applications which utilize those keys. So as I said at the beginning of my presentation, this one picture is for another presentation, how to deal with the management layer and application layer. What I will say now, it's very interesting that for the management layer, the SDN approach, I think is the best right now, because you can do in real time the optimization, for example, of the parameters of the QKD devices. You can also, when you have more complex network architecture like this, not a straight line, you can do some turnarounds. So for example, you can go from Alice to Bob using the intermediate node on the other route based on the parameters of the network. But moving on to the coexistence with classical communication, those are the results from the paper published on International Conference on Optical Network Design and Modeling. I think they are very interesting because what they did, this is a very small image, but you have those two charts which have those greenish thingies. Those are the spectrum allocation of quantum and classical channels. On the left side, you will see one peak. This is only quantum channel. And on the right side, you have in the middle one quantum channel, and to the left and to the right, we have the classical channels. So they tried to pass the quantum channel standalone, and they measured the effects of the coexistence of the classical and quantum channels. And what they showed that when they increase the channel power of the classical signal, it increases the noise which is present in the network. So it lowers the distance which for which the key can be generated. So this small r thing corresponds to the final secret key length, which is divided by the total number of exchange signals. So the green area is the area where the accurate is the key generation is possible. The orange one is where this is not possible. And when we look at the A chart, we see clearly that when there is only quantum channel in our network, the Xi, this is the excess noise, the noise, the noise which is present in the network is lower than when we move on with the power level of the classical channel. So minus 30 dBm power of the classical channel is this orange line, and this yellow is for minus 10 dBm. So you can clearly see that there is this trade-off between the existence of the quantum channel and the power level of the classical channel, which influences the bit error rate of the classical communication. They showed also that when they move on with the power level of the classical communication to the 0 dBm, there is we cannot talk about the key generation, so the noise is too big, and we have many sources of the excess noise. The most important for the CVQKD is the spontaneous Raman scattering. We have also the noises coming from the MUX devices. The next one, namely relay scattering for wave mixing, they are not as big as, for example, spontaneous Raman scattering, but they are there and they add up to the summary excess noise. We have also the problem with the amplified spontaneous emission, the EDFA amplifiers. And what we can do, we can try to find a gap band between the position of the quantum channel and the position of classical channel. When the gap is enough to not to lower those effects which I showed here, we can have a coexistence of those two types of signals. But this also influences, the cost of the quantum channel, because we need to delete, for example, one classical channel from our communication. But when we, for example, do a band gap, for example, for 200 gigahertz, the communication is possible also for the higher levels of the power of the classical communication. So this is very complex. This is the one side of the coexistence with classical communication, and I didn't mention the problem of environmental problems, for example, from the temperature, the vibrations, and so on. So it also will influence the secret key rate. But this existence is possible. So from our perspective, from the telco operator perspective, this is very good. Moving on, where we can, in what ways we can use the QKD in telco networks. We can focus on the QKD in fiber using the trusted relay architecture, like I showed before. The useful distance here is about 100 kilometers between nodes. It can be increased using trusted nodes, but they need to be controlled. So this also influences the use cases, because you need to have trust into the operator, and you have to have trust for the devices. There are also QKD in free space. Namely, we can do this using free space optics. It is possible to transmit keys over long distances, and also the satellite to ground QKD. The source of those images is a very interesting paper. It is quite old one, but it shows that this is not the case, that we need to choose. For example, we are using only QKD in fiber, but we are not interested in QKD in a free space or in satellite. Why? It depends on the part of the network which we want to cover. When we have metro networks or local networks, when the distances are not so big, we can use QKD in fiber. But when we want to build a bigger network or we want to move on to the scale, for example, for thousands of kilometers, we should combine the satellite QKD with the QKD in fiber. So it depends what type of network we want to create. Moving on to use cases, we have a constant discussion. What use cases? I found that, for example, the QKD could be used to secure data center interconnection, like in banking or government. There is also a strong work to use QKD as a security layer for the data transmitted over the 5G, 6G mobile networks, also securing financial transactions and blockchain systems. The QKD as a service business model. So for example, we can sell the keys or sell the encryption. to our customers. The integration of the SDN solution is also very interesting because the SDN could be not only used to deal with the QKD, but also when you have the SDN solutions, you can use QKD to encrypt the management informations which are moved between SDN devices. The very interesting topic is the hybridization of PQC and QKD. So we can combine PQC and QKD to have more than one layer of the quantum resistance in our network. And there are many more, but there are problems to solve. When I talk to guys in our company, in our other companies, I think the most important problems to solve are the trusted node architecture to lower the assumptions for the trusted node. And also there is the last mile problem. So for example, when I have a mobile phone, I can't have there a QKD device, to obtain the keys. I need to transmit those keys wirelessly. And there is a trade-off between the 100% of security based on the quantum key distribution and the mobility of the devices. What are the advantages? To sum up, what are the advantages and challenges in using QKD? So the benefits is the security is based on the laws of quantum mechanics. So the underlying security proof do not depend on the computational power of attacker. So we do not believe that in the next 20 years there will be not enough computer power to break our communication. We have this covered. The detection of eavesdropping in real time. So the eavesdropping in QKD, when you have the noise level more bigger than a certain threshold, you believe that there is eavesdropping. The resistance to future threats from, for example, quantum computers, which I think is not that far away, that many of the people believe that there will be, for example, 20, 30 years. I think that it will arrive much, much faster. It is not prone to store now decrypt later attacks. Because of that, when you have a certain use cases, when your data is you need to be secure, for example, for 20, for 30 years, I think today it's too late to deal with this because the future is coming very fast. The challenges are the high hardware costs and the need to upgrade current infrastructure. There is no need to build a whole new, brand new QKD infrastructure, but we need to upgrade the current infrastructure. For example, we need to change the points in our infrastructure to cover those trusted relays. The limited coverage via fiber optics, and also the sensitivity to environmental conditions. The challenge is also the coexistence with classical communications, but what I showed, it proves that it is possible. But the business perspective from my side, I think it's pretty good because it increases data security, it gives the highest level of protection, and also this is very important that it ensures the compliance with legal and regulatory requirements. So not only quantum computers, we should not talk only about the threat from quantum computers, because the other guy, you could say, but it will arrive in 20 years. But you can say that, okay, but QKD is also answer for the regulatory requirements of the safety of the data. And this is the case. So thank you very much, and I open for your questions.
Thank for you watching these presentation highlights, and thank you for being a valued member of our community. We hope you enjoyed this presentation.